Hey, chemistry crew, Mr. Collier here. We're going to take some notes today. If you have a chemistry packet from me, this is on page 4 in that packet. We're going to be talking about measuring gases. And throughout this chapter, as we talk about the calculations that go along with gases, there's going to be 4 variables that can show up. Not every equation uses all 4 variables, but we will be using all 4 of these as the chapter continues. So the first variable is the amount of gas that we're talking about. Obviously, if you have more or less of a gas, that's going to affect the calculations that we do when it comes to that mass. So this is going to be measured in the amount of gas, as in moles. So how many moles of this gas do we have? And so you might find yourself doing some molar mass calculations as we go along here. The second variable is volume, which can be measured in liters or milliliters. As we get into specific equations, we'll talk about whether one of those is required or not. The next thing, the next two, come in the form of STP. So when we say STP, and we've said this before, we're talking about standard temperature and pressure. So temperature and pressure are going to be the last 2 variables that we talk about. Temperature is going to be 0 Celsius when it's standard, or 273 Kelvin when it's standard. So if a problem says at STP, you now know what the temperature and the pressure are, and the temperature is going to be 273 Kelvin. Now, just a quick refresher on converting to Kelvin, because we are going to be doing most of our calculations here in Kelvin. You're going to start with Celsius and simply add 273 to it. So 22 plus 273 gives you 295. 100 plus 273 gives you 373. And these are, again, going from Celsius to Kelvin. It doesn't matter if you start with a negative Celsius. Celsius can be negative, and so we can start with a negative. We still simply add 273 and get our new value. The lowest you can have in Celsius is negative 273, because if you add 273 to that, you get 0 Kelvin, which is that absolute 0, the coldest possible temperature. Anything less than negative 273 Celsius would be impossible. As I mentioned, that last variable is going to be pressure, abbreviated with a P. Pressure has lots of different units, and the standard pressure is going to be 1 atmosphere, but there's lots and lots of different units for pressure. So what an atmosphere is, and we'll talk about this a little bit more on the next slide, is it's the amount of pressure that our atmosphere exerts on something that is sitting at the surface of it. And that can be converted to a lot of different units. So millimeters of mercury and torr are the same. And I'll talk a little bit about where that millimeters of mercury as a unit came from when I show you a slide of a barometer in just a couple minutes here. Pascals and kilopascals are kind of the metric standard, so we have to put those in. Pascals, as you can see, it's a huge number, 101,000. So we typically talk about kilopascals instead, but that's a sort of metric standard. And the English equivalent is pounds per square inch. And this, I think, is the one where everyday American students here can start to understand how much pressure this really is. So the atmosphere exerts 14.7 pounds on every square inch of your body. I'll talk in a few minutes about a little demonstration that can be done with this. Now, with all of these different conversions, these values, we have a bunch of different conversions that we can do. So we can convert between any of these units, which is going to be what we do with this set of notes. So for example, say we wanted to convert from 1.026 atmospheres to kilopascals. So we're starting with atmospheres. We want to go to kilopascals. We know that there's 101.325 kilopascals in 1 atmosphere. So I set up my conversion factor with the thing I want to end up with on top and the units I want to cancel out of on the bottom. The numbers then just come from these numbers that I've given you here. By the way, these numbers are also, I believe, in your reference packet, so they're not numbers I'm asking you to memorize. I'm just asking you to be able to use them to make these conversions. Now we multiply across, cancel out our units, and we'll have our new value. Keep in mind that whatever number of significant digits your original value had is how many we want to give in our final answer. We are assuming that our conversion factor has an infinite number of significant digits, and that our value that we started with was the one that was limiting our ability to say how many significant digits we had. Here's another example, again, also in your packet. 98,500 pascals, so that's pascals here, and we want to convert that to millimeters of mercury. Now in this one, neither of the numbers in the conversion factor are going to be 1. In fact, if you look at all these values, the only one that has a 1 is 1 atmosphere. Everything else has values with it. So we're going to put millimeters of mercury on the top. That number is 760. And we're going to put pascals, the number that goes with that, 101,325. We're going to put that on the bottom. The pascals cancel out. I multiply 98,500 by 760, get an answer, divide that by 101,325, or just put it into your calculator with parentheses and do it all in one step, and you'll get the conversion factor. There we go, our final answer. So we do those conversions just because there are so many different units we can use to measure atmospheric pressure. Because atmospheric pressure is a big deal. A lot of different people use it for different reasons, which has given us lots of different units. It is, as I said, the amount of pressure exerted by the air in the atmosphere, and it varies with altitude. So when we say standard pressure, we are saying at the Earth's surface, what we call sea level. As you go up, the pressure will go down, and we can calculate that as well. It also varies not only with altitude, but also with water vapor content, because the different gases in the atmosphere have different relative weights and will give you slightly different pressures on the surface. We're not really going to get into vapor content in our calculations here, but it is pretty impressive to think that if you take a column of air that is simply 1 square inch and trace it all the way to the edge of our atmosphere, it's going to have this huge mass, and it's going to exert a large amount of pressure on you. A really cool demonstration we can do with this is take a can, like a soda can that's empty, put a tiny little bit of water in it, heat it up, flip it upside down into some cold water, and you'll see the can get crushed under the weight of our own atmosphere. It's pretty impressive that our atmosphere has so much pressure it can exert. One last thing before I set you loose to work in your packet. Where did that number millimeters of mercury come from? What's up with that? So atmospheric pressure can be measured with something called a barometer. This is a sealed glass tube. It's sealed on one end and open on the other. And traditionally, it was filled with mercury. And they put a little vacuum in here, meaning there's no air in the top. And the atmosphere will push down on the mercury, pushing it up into the tube. And as the atmospheric pressure changes, if it pushes more, the mercury rises. And if it pushes less, the mercury sinks. And we can measure, based on the height of the column of mercury, whether atmospheric pressure is higher or lower. Now, we're not going to get into meteorology, but obviously this has a large effect on whether the weather is going to be nice, whether it's going to rain, etc. We can look at the relationship there. So what you're going to do now is work on page 5 in your packet here on gases. And if I go back just a second, what that is going to look like is a lot of these conversions. So you're just going to get practice converting, and then I'm going to set you loose with some new equations in our next video. So thanks. Good luck. Let me know if you have any questions.